All right, this video is going to show how to do a titration curve, specifically calculations of titration curves with a weak acid and a strong base. All right, and then on the bottom of our sheet, we are going to graph it. Okay, so we have A, B, C, and D only. We have four scenarios that we need to kind of figure out. If you were really trying to be accurate, you probably would do a little bit more, but this is enough for us. So I'm taking 50 mils of a 0.1 molar acetic acid, which is a weak acid, and we will need to know the Ka. It's 1.8 times 10 to the negative fifth, with a 0.1 molar NaOH. Just so you have an idea, is then you should be able to visualize this titration curve. So like on this first problem, it says no NaOH and 50 mils of a 0.1 molar HAC. Please understand that AC is short for acetic acid. So if I were going to do my titration curve, or my titration setup, and again, sorry, I'm using a mouse pad here, is that I probably have my weak acid here, and this is where my strong base is. And the reason why I know that is that I'm given a scenario where I have the acid already. Also, you know, the last thing that I realized that I know that I have that you should recognize is that I have an amount of my weak acid. I do not have an amount of my strong base. And that is because I'm going to continually add more of it. Okay, so we need to find the pH for each of these, and let's get going. So this first one, if I just have 50 mils of a 0.1 molar solution of a weak acid, that is a classic weak acid problem. So weak acid problem, I have something like this, right? That's my dissociation equation. I have 0.1 molar, I have 0, 0. So I'm going to do something like this. A lot of you, I hope, look at this and go, oh, that is going to be x squared over initial minus x equaling my Ka. And we'll take a look at that. So here I go. This should look very familiar. X is going to equal my H plus. I get that. What am I going to do with it? I simply plug it into pH equals negative log of my equation. And voila, I have my pH. So why don't we go plot that right away? Just so that we can keep this going and understand where we are in each point. So I have 0 milliliters of NaOH, and my pH is 2.87. So what I did here, again, it's a little sloppy, but I basically have, I estimated where the 25, 50, and 75 are, because I'm going to 75. And then I want to make sure that I place pH, so 1, 2, 3, 4, 5, 6, whoops. That is off a little bit. 7. Huh. Okay, so there's going to be my 7. So this whole side is going to be pH, and this will be the amount of OH added. So I was at 2.87 with 0. So I'm at 0, 2.87, about there. All right. Let's keep going now. What happens, because these are harder than a strong acid, strong base. What happens when I add 10 milliliters of NaOH? Okay, so this is what you have to think about. I have my acid. I have my base. Okay? What is that going to make? Well, an acid and a base always still makes water. What's left over? Just looking at that right now. Well, if I take the H and I take the OH, I hope that you go, oh, well, the AC minus would be left, which is, again, the C2H3O2 minus. So you have to do this in moles. That's why millimoles works really well. So let me show you what I'm going to do here. I'm going to take 50 mils of my 0.1 molar solution, 50 mils of my 0.1 molar solution up here. Right, and that's going to give me 5 millimoles. I'm going to take 10 milliliters of a 0.1 molar solution, because I have 10 milliliters of a 0.1 molar solution. And that's going to give me 1 millimole. So what happens when acids and bases react? Acid bases react and consume. They neutralize, right? They create water. So what I'm going to do is say, take the least amount, and when the OH runs out, it's gone. And what's left is I'm going to have 4 millimoles of my HAC, and I'm going to have 0 millimoles of my OH minus. So now I know my change. So this is important. Water is obviously not going to be included because it's a liquid. I start with 0, right? So now I'm going to add 1 millimole, and now I have 1 millimole left. All right, now I need to put this into some sort of an equation. So the easiest way to do this is using Henderson-Hasselbalch, okay? So there's many ways you can do this, but if you put it over the total volume, so I have 10 milliliters of my base, but where's that 50 from? My initial acid, okay? I'm going to have 0.0667 molar of my acid. Same thing here. I do it over the 60. I've proven that that's 60, and I'm going to have 0.0767 of my conjugate base, okay? So there is an equation. It's called the Henderson-Hasselbalch equation. It is so much easier to use. If I just say pH equals pKa plus log of base over acid, this is what it's going to look like. So I take negative log of my Ka. That's pKa. So the Ka we got from the top, 1.8 times 10 to the negative fifth. And I add it to a log of my base over my acid. Which one's my base? Which one's my acid? Well, this is my acid. This is my conjugate base. So I hope, looking at the numbers, and pause whenever you need, there's my base, there's my acid. This relationship works out really well, and I get 4.14. So it should make sense. I'm adding base to my acid. It's going to become more basic. So let's go down and plot this now. So I have 10 milliliters, 4.14. So 10 milliliters, we're going to go right roughly there, 4.14. So 1, 2, 3, 4. So that's going to climb pretty quick. Okay. Again, I would love to do more than these 4 points. You really need about 5 or 6, but I'm just trying to show you the main parts of this. Okay, so what happens at 50 mils? So here we go again. I have my equation. Right? So I already knew I had 5 millimoles because I had it before. It never changes. Whatever's in the Erlenmeyer is never going to change. Now I have 50 mils of a 0.1. So 50 mils at a 0.1 is 5 millimoles. Uh-oh. Well, 5 millimoles and 5 millimoles are equal. But what you got to realize is that reaction's still driving to the right. I'm still making water. So we're not going to use that in our equation, but both sides are going to be adding 5 millimoles. So when I'm all done, what I have is 5 millimoles over 50 plus 50. So I have 0.05. This is the hardest step. And the reason why is because this is the equivalence point. And the equivalence point is a tricky situation. Okay, couple facts. One, if you don't have H plus or OH minus on the right side, you cannot calculate pH. Unless, fact number 2, you have a conjugate pairing with amounts, like here, where I have the acid and its conjugate base. Then I can plug it into Henderson-Hasselbalch equation. But in this case, I do not. So what has to happen, think about this for a moment. See how I only have one arrow? The reaction is driving it to the right. It's flooding it to the right. Kind of think of it as a tsunami. The water goes and gets pushed one way. The problem is, it's got to come back. Okay? It's got to come back this way. So you can think of it literally like the reaction is going to change and switch directions. So you just rewrite it, but you rewrite it, I don't know what's happening here, going in the opposite direction. So now I'm starting with the 0.05. I don't have OH, and I have zeros of these, right? So I have minus X. This is a normal problem now. Minus X, I have X, and there I am. Just take a look at that. That should resemble a lot of things that we've been working on. So now, what you got to realize, though, is that you need a KB. You are in an environment that is basic, not acidic any longer. So that is extremely important. That's why this problem is so much more difficult than any other step. So we need a KB. So what I'm doing now is I'm plugging this in. Here's my KB now, and here's my expression. So x squared over initial minus x, and I plug that all in. X now equals OH minus, like we've done. So then what can I do? I can basically say that POH equals 5.828. You should go, whoa, that doesn't make any sense. That's acidic. So I need to make it basic. So At 50 mils, I have an 8.72. So let's go do that. At 50 mils, I have an 8.72. So 7872 right there. Okay. All right. Now, there are many more points that we could do, but I'm just trying to show you some calculations. In the next video, you can watch some of the more specific things that we can figure out. So here's the last one. Now I'm going to go past the equivalence point. I know I'm past the equivalence point. So now I have this equation right here. And again, why am I not calculating the millimoles for the acid? Because I already know how much I have. It doesn't change. Now I'm adding that much OH. So now I have 7.5 millimoles of base and only 5 millimoles of acid. So I'm actually going to subtract the 5. So what I have left is I have more base than I have acid. It drives it to the right. And here's the one thing. You're going to look at this, go ahead, Henderson-Hasselbalch. What you got to realize, though, guys, is that this is a strong base. That's pure OH. This is a weak base. We don't know how much that's actually going to provide, but it's never going to be as much as the strong base. So when you have excess strong base, all you need to do is take that value. So I am only taking that value. So this is the millimoles over the milliliters is 0.02 molar. So I'm taking a negative log of that. And my pOH is going to be 1.7, and my pH will be 12.3. So let's plot that one. So at 75, I have 12.3, so 7, 8, 9, 10, 11, 12.3. Okay, so now there's one thing that if you look at your reference sheets that we didn't figure out on this one, but I have it on our next video, is that there's a plateau that happens here. There's a rapid increase with a weak strong. Remember, strong looks like this. For a curve, but a weak strong looks a little different. So you're going to have a plateau, and it's actually a pKa. We can figure that out later. But what happens is that this usually flattens out, and then it goes up, and then it comes out hard like that. So, and I'm going to try to draw that one more time. And this is really tricky for me. So it increases in the beginning, and as it's increasing, it's creating a buffer. And then it resists pH change, and then it breaks. We're going to talk all about this. So right here is where it resists the pH change, just so you know. And because this is at 50, exactly at 25, we're going to learn that that's called the pKa. And that is just the negative log of my acid or my base equilibrium expression. And then you just take half of the amount. So we could actually figure that out at any time. And that'll be in our next video. So this was a strong base, weak acid. Notice the difference. It has a increased slope. It levels off. This is our buffer region, we call it. And then this half looks a lot like a strong.